So now we want to prove this lemma. For that, let's recall a function f is submodular if fx intersection y plus fx union y is smaller than or equal to fx plus fy. And as we checked before, this delta is a modular function. So here, how do we prove this lemma? Is that if a graph is minimally th connected, that means once we delete an edge, then it is no longer th connected, right? But what does it mean to be th connected? Th connected means that for every x, a vertex set, the number of edges leaving it is at least t. But once you delete an edge, then it is no longer th connected. Means that there exists a set which exactly t edges are leaving. But once you delete xy, then it's no longer th. So in minimally th connected graph, there exists a vertex at x which has exactly th is leaving from x. And if this x happens to be just one vertex, then we are done. There is one vertex which has exactly degree t. So we want to show that if we take a minimal such set with degree, edges leaving there is exactly t. Among those, we take the minimal one, and then we want to show that this is actually just one vertex. So let's be a minimally th connected multigraph. If delta x is at least, bigger than t for all non-empty proper subset, then we can delete any edges and still have th connected multigraph. So delta x equal t for some vertex at x. And before proving that, smallest one has the one vertex, let's show that what happens if there is an edge inside. Suppose that gx has an edge xy, so we have x and there is x and y. Since if we delete this xy, then it is again not th connected because this is minimally th connected. That means there is a non-empty set G, which is non-empty proper subset of the vertex set, containing exactly one of xy such that after deleting it, the number of edges leaving G is less than or equal to t minus 1. And since, in the original graph, this is at least t, so this is at least t minus 1, so delta of G is exactly t. Then, by the submodularity, of this function delta, what do we have? X intersection G and X union G. If you sum it up, then that's at most, G, delta of G plus delta of X, which is 2t, which implies that, so this is because G is TH connected. Any set has, delta value at least t. So, delta of X intersection G is t, and G contains exactly one of X and Y. So, G intersection X is smaller than X. So if we take a minimal set X such that the number of edges leaving this is t, then this shows that this must be an independent set. So X is an independent set. What if it has more than one vertex? We know that each vertex has degree at least t, because it's TH connected graph. Each vertex of X has at least t incident edges leaving X. We have X is 1, because the number of edges leaving here is size of X times t, and then we just assume that this is t. That means X is 1, and this is the desired vertex of degree exactly t. So which proved the lemma. Now let's prove the orientation theorem. So what was the theorem? Theorem is that a multigraph has KH connected orientation if and only if this is 2H connected. So if there exists a H connected orientation, then for any cut, we have to have at least K edges to this direction and K edges to this direction. So as an undirected graph, there are 2 edges in any cut. So as a undirected graph, this must be 2H connected. So this direction is easy. And let's consider the other direction. So we use induction on n, the number of vertices. For n is 2, then what do we have? We have 2 vertices joined with more than 2k vertices, 2k edges. So we can easily check that the theorem holds. So let's assume n is bigger than 2 and consider 2k edge connected. multigraph. And we can just delete some edges and then find the orientation and then add back the deleted edges with the arbitrary orientation. So it suffices to find the KH connected orientation of minimally 2KH connected. Multigraph. So by the previous lemma, there exists a vertex G of degree exactly 2k. And we apply shortcut lemma. We apply it iteratively, find shortcut of G until we reduce the degree of G to 0. And while doing that, this maintain 2k edge connectivity, connectedness, say, relative to G. And at the end, we have a vertex G with a degree 0, and we delete G is 2k edge connected multigraph G prime with n-1 vertices. By the induction hypothesis, G prime has a KH connected orientation, say D prime, and we orient G by replacing its shortcut at UV with the path UGV or PGU, which agree with the orientation of UV in D prime. So now we need to check that this orientation actually give us a KH connected orientation. For that, what we have to check is that for all non-empty proper vertex at X, the number of edges leaving X is at least K. As long as this X is not G, or the complement, let's just say, anyway, as long as this is not that, this, let's say lifting UV, meaning that we have UV, we change into UGV. This preserves this in the orientation. The only edge lost is UV, and if UV leaves X, then UG or GB is a new edge leaving X, depending on whether G is in X. Give me a moment, sorry. There was some typo that I wrote. Wait. Yeah. So as long as X is not G itself, we know that after this lifting, the number of edges leaving X is still same. Because if this contains both U and V, then here again, it's in U and V. Okay, let me put it this way. So only edge lost is UV. And if this edge is lost, that means the X contains U but not V. But if it also doesn't contain G, U, G, V, then this edge UG is a new edge that was not in here. Say G was a isolated vertex here. And if it contains G as well, then this UV is lost, but now we have GV UH. So it's preserved. And after K leaves, we also have that the out degree of G is K, and the out degree of the rest is also K. So delta X is at least K whenever this X is non-proper, non-empty proper subset of G. So the resulting orientation is KH connected, and this proves the theorem. So this finishes the proof of the Nash-Williams' orientation theorem. So today we show that when we have a 2H connected graph, then we can orient the edges so that the resulting graph is TH connected. Thank you for listening.